The date was October 21st, 2025. Inside the main mission control center, the air felt heavy, much thicker than usual. It was not the heat, because the environmental control systems were humming at a steady 20 degrees Celsius. It was the weight of the weight. Dozens of men and women sat in front of long rows of glowing monitors. Usually this room was a place of controlled chaos, filled with the sound of voices sharing urgent data, the rapid clicking of mechanical keyboards and the flashing of green and red status lights. It was a place of action, but today the room was almost completely silent. The only sounds were the low rhythmic hum of the computer towers and the occasional nervous cough from a scientist. Everyone's eyes were locked on the main screen at the front of the room. They were watching a digital simulation of the solar system. On the massive screen, a small blue dot represented the Earth. A massive burning yellow circle represented the Sun, and far away on the very other side of that fire was a tiny grey marker labelled 3I Atlas. This was the moment they had spent months preparing for, but it was also the moment they secretly dreaded. It was the beginning of the solar conjunction. In the simplest terms, the geometry of the universe was working against them. The object known as 3I Atlas was moving along its specific orbit, and today it was passing directly behind the Sun from the perspective of Earth. Imagine holding a small glass marble at arm's length, and then having a large person stand directly in front of you, completely blocking your view of the marble with their body. Now replace the person with a massive star that burns at millions of degrees, and replace the marble with the most mysterious object humanity had ever discovered. For the past few weeks, the radio signal from 3I Atlas had been strong and clear. The object had been sending back streams of incredible data, high-resolution pictures, surface temperature readings, and strange magnetic signatures that the physicists were still trying to understand. It was a river of knowledge flowing from space down to Earth. But as 3I Atlas moved closer to the visual edge of the Sun in the sky, the connection began to struggle. The Sun is not just a quiet ball of light, it is a noisy, violent beast. It blasts out radiation, solar winds, and radio waves that act like a wall of massive static noise. Trying to hear the electronic whisper of the 3I Atlas transmitter over the roar of the Sun was like trying to hear a pin drop in the middle of a thunderstorm. The lead flight director stood up slowly from his leather chair. He smoothed out the wrinkles in his white shirt, but his hands were shaking slightly. He looked over at the communications officer, a young woman who had not blinked in several minutes. "Status on the downlink," the director asked softly. "Signal-to-noise ratio is dropping rapidly, sir," the officer replied. Her voice was steady, practiced, but tight with tension. "We are losing data packets. The files are arriving corrupted. The Sun is drowning it out." On the big wall screen, the digital line that represented the connection quality turned from a solid, healthy green to a flickering yellow. Then a few seconds later, it flashed a warning orange. 3 minutes to full occultation, someone announced from the back of the dark room. Full occultation. That was the scientific term for hidden. It meant the object would be physically behind the body of the Sun. There would be no line of sight. No radio waves could travel through the star. For the next several days, Earth would be blind. It was a strange, humbling feeling for the people in this room. They were the best scientists and engineers on the planet. They had built machines that could think faster than any human brain. They had built telescopes that could see light from the beginning of time. They had radars that could track a metal screw falling from a satellite thousands of kilometers away. Yet right now, they were completely helpless. They could not move the Earth to a better viewing angle. They could not turn off the Sun to stop the interference. They simply had to sit there and let the laws of physics take away their greatest prize. Far away from this room, out in the deserts of California, Spain, and Australia, the giant white antenna dishes of the Deep Space Network were slowly tilting. These massive mechanical ears, which usually listened to the faint whispers of robots at the edge of the solar system, were useless for this specific task now. If they pointed directly at the Sun to try and find 3I Atlas, the solar radiation would be too intense. The heat and noise would overwhelm the sensitive receivers. They had to look away. One by one, the great mechanical dishes stopped tracking the object. They went into safe mode, staring at the blank blue sky or the ground. It felt like a surrender. 1 minute, the voice from the back said. The atmosphere in the mission control room shifted from high anxieties to a sort of sad acceptance. The scientists looked at their personal desktop screens. The numbers were freezing. The live feeds of data were stopping one by one. The stream of information, which had been flowing like a powerful river for months, was drying up into a trickle. "Signal is critical," the communications officer said, pressing her headset tighter against her ear. "We are receiving mostly static now. I cannot distinguish the telemetry." The flight director crossed his arms over his chest. He looked up at the ceiling as if he could look through the roof through the atmosphere and see the sun burning in the sky. He thought about the object out there. It was all alone. It was entering the dark, hot shadow behind the star. There was a profound irony in this moment that everyone felt. Humanity had created a world where information travels instantly. We can send a message to the other side of the globe in a split second. We are used to being connected 24 hours a day. If a phone call drops, we get annoyed. If the internet is slow, we get frustrated. We have forgotten what true silence feels like. But space does not care about our technology or our impatience. Space is vast, and the distances are so great that they crush the human ego. In the face of the celestial mechanics, the turning of the giant planets and the burning of the stars, our best technology was nothing. We were just children waiting for the adults to move out of the way so we could see our toy again. Loss of signal in 5, 4, 3. The room held its breath. No one moved. 2, 1. The main screen flickered once. The jagged line that tracked the electronic heartbeat of 3i Atlas went completely flat. A message popped up in simple white text against a stark black background, no carrier signal. "Signal lost," the officer confirmed, taking off her headset and placing it on the desk. "We are in the blind." Absolute silence filled the room. It was a heavy physical silence. For the first time in months, there was no new data coming in. 3i Atlas was gone. It had not been destroyed, it was just hidden. But the psychological effect was immediate. It felt as if the object had vanished into a void. The flight director exhaled a long, slow breath. "Okay, people," he said, his voice breaking the spell. "Mark the time. We are officially in the conjunction phase. We expect to reacquire the signal in 72 hours. Until then, we wait. Keep the systems warm, run the trajectory simulations. But for now, there is nothing we can do." He sat back down, but he did not look away from the blank screen. The blindness was total. It was not just their own antennas that were useless. The Hubble Space Telescope, orbiting high above the Earth, could not look anywhere near the Sun without damaging its sensitive glass mirrors. The new giant optical telescopes on the high mountains of Chile were also blind to that bright sector of the sky. For all the power of human civilization, for all our pride and our inventions, the simple alignment of spheres had defeated us. The mystery of 3i Atlas suddenly felt deeper and more frightening. Before, when the data was flowing, it was a scientific problem to be solved. It was just numbers, charts and graphs. But now that it was silent, it became a ghost. What was happening behind the sun? Was the object changing its shape? Was it speeding up? Was it slowing down? Or was it doing something else entirely, something that the laws of physics said it should not do? Without eyes on the target, the human imagination began to fill in the blanks. And in the quiet of that control room, the imagination was a dangerous thing. The scientists shifted uncomfortably in their chairs. They drank their cold coffee. They checked systems that did not need checking just to keep their hands busy. They were not just waiting for a machine to beep. They were waiting for a reassurance that the universe still made sense. Outside the building, the sun shone brightly in a clear blue sky, warm and life-giving to the plants and trees. But to the people inside the room looking at the black screens, the sun looked different today. It did not look like a giver of life. It looked like a heavy curtain that had been pulled shut, hiding the most important thing in the world from their view. The wait had begun. The vanishing into the void was complete. Now there was only the silence and the digital clock on the wall ticking slowly toward the future. To understand why the ship goes silent, we must first look at the simple but unforgiving rules of how things move in space. This situation is not the result of a broken computer or a damaged antenna. It is caused by a specific alignment of the planets and stars known as a solar conjunction. In the simplest terms, a solar conjunction happens when a planet or a spacecraft travels to the opposite side of the Sun from the Earth. Imagine a straight line drawn through the solar system. At one end of this line is the Earth, where the mission control team sits waiting for a signal. In the exact middle sits the Sun, massive and roaring. At the far end of the line, hidden completely behind that burning star, is the ship. This alignment creates a perfect geometric block. This is not a rare or unexpected event. It is a standard part of celestial mechanics, the giant clockwork of our solar system. Because Earth travels around the Sun much faster than the outer planets or ships, travelling deep into the void, we constantly lap them on our orbit, or we get stuck on the opposite side of the track. When this happens, the Sun becomes more than just a source of heat and light. It becomes a massive physical obstacle. You might ask, why is the Sun such an impossible barrier? We send signals through walls, buildings, and even mountains on Earth all the time. Why can we not just shoot a radio signal through the fire of the Sun? The answer lies in the violent nature of the Sun itself. The Sun is not a solid rock like the Moon or Mars. If it were just a quiet ball of solid matter, we might be able to send a signal around the edge of it with relative ease. But the Sun is a ball of violent superheated gas and plasma. It is constantly exploding. It breathes out a massive cloud of charged particles known as the solar wind. This creates an environment that is incredibly loud in terms of energy. The Sun emits radio waves across almost every frequency imaginable. To a sensitive radio receiver, the Sun sounds like a massive amount of static noise, like a scream that drowns out a whisper. When the ship passes behind the Sun, its delicate radio signal, which has travelled millions of kilometres and is already very weak, must try to pass through the Sun's outer atmosphere known as the corona. The corona is a chaotic soup of high-energy plasma. When the ship's radio waves try to pass through this plasma, they get distorted. Imagine trying to look at a coin at the bottom of a swimming pool while someone is splashing the water violently. The image of the coin wobbles, shifts, and breaks apart. This is exactly what happens to the radio signal. It suffers from heavy interference. The data stream becomes garbled. A message that should say all systems normal might arrive at Earth as a meaningless string of random noise. This phenomenon is well documented in real history. We can look at the exploration of Mars to understand the reality of this danger. Every 2 years, Mars and Earth experience a solar conjunction. Mars goes behind the Sun. When this happens, NASA and other space agencies have to fundamentally change how they operate. They do not just keep working as usual, they essentially shut down the conversation. For a period of about 2 weeks, controllers on Earth stop sending commands to the Mars rovers like Curiosity or Perseverance. This is called a command moratorium. They do this because of the high risk of a corrupted signal. If a controller sends a command telling the rover to drive forward 10 meters, and the solar interference changes a few bits of that digital code, the rover might interpret it as delete main operating system or drive off this cliff. The risk is simply too high, so the most advanced robots in human history simply go into a sleep mode and wait. They sit alone in the red dust, completely cut off from their creators, waiting for the geometry of the solar system to change. For a human crew, however, this experience is far more terrifying than it is for a robot. A robot does not feel lonely, a human does. As the ship enters this alignment, the crew witnesses the geometry of shadows firsthand. From the window of the spacecraft, the Sun begins to dominate the sky. It grows larger and larger as their trajectory brings them closer to the star's visual edge. This creates a scene that is simultaneously the most beautiful and the most frightening thing a human can witness. The beauty comes from the light. The solar corona creates a glowing halo, a shimmering crown of pearl white and gold light that dances around the black disk of the Sun. It is a spectacle of raw power, but that light is the very thing that is blinding their communications. As the ship slips behind the star, the Sun literally swallows the Earth. One moment, Earth is a bright blue spark in the distance, a symbol of home, safety, and family. The next moment, the rough edge of the Sun creeps over it. The blue spark vanishes into the overwhelming glare of the solar fire. This moment marks the beginning of the zone of silence. For the observer on Earth, the ship simply ceases to exist. The telemetry screens go blank. The heartbeat of the data stream flatlines. There is no static to listen to, just an empty void where a ship used to be. The mission control room becomes quiet as there is no data to analyze. For the crew, the silence is heavy and physical. They look at their communication panels and see the no carrier warning blinking. They know that even if they screamed into the microphone, their voices would only travel as far as the solar winds before being shredded by the Sun's interference. They are deep in the shadow of the star. This geometry creates a profound sense of isolation that is hard to describe. In deep space, the only thing connecting an astronaut to their humanity is that thin invisible thread of radio waves reaching back to Earth. When the Sun cuts that thread, the crew realizes how small they truly are. They are floating in a metal shell behind a distinct ball of nuclear fire, hidden from the view of everyone they have ever loved. The Sun, usually the giver of life, becomes a jailer. It creates a wall of interference that is thousands of kilometers thick. The laws of physics are absolute here. No technology we currently possess can punch a clear signal through the center of a star. They must wait. They must let the mechanics of the universe play out. They have to wait for the ship to drift along its curved path until it clears the edge of the solar disk. Until that geometry resolves itself, they are ghosts. They are alive, breathing and thinking, but to the rest of the universe, they have disappeared into the blinding light. This is the terror of the solar conjunction, the realization that in space light can be just as impenetrable as a stone wall. Looking back now, after the object has vanished into the dark, we must sift through the digital ghosts it left behind. When we open the archives from early 2005, we are not looking at a simple rock. We are looking at a puzzle that challenged everything we thought we knew about how comets behave. To understand the massive void that 3I Atlas left behind when it disappeared, we must first understand what it looked like when it was fully alive in our telescopes. We need to reconstruct the face of the stranger. Between January and May of 2025, the data did not make sense to anyone. Astronomers all over the world were arguing in observation rooms and online forums. Usually when a new object appears in our sky, we can quickly categorize it. We ask simple questions. Is it an asteroid made of rock? Is it a comet made of ice? But 3I Atlas was shy. It refused to fit into a neat box. In the early months of the year, as it moved silently through the cold space between the orbits of Jupiter and Mars, it began to wake up much earlier than any standard comet should. The first strange feature was its shell, or what scientists call the coma. This is the fuzzy cloud of gas and dust that surrounds a comet's solid core. For a standard comet born in our own solar system, this cloud usually forms only when the object gets close to the sun. The heat of the sun melts the frozen water, turning it into steam. However, 3I Atlas developed a thick, bright sheath of gas while it was still very far away in the deep freeze of the outer solar system. This told us immediately that the ice on its surface was not like the ice we have on Earth. It was highly volatile, ready to explode into gas at the slightest touch of warmth. It was reacting to sunlight that was still too weak to melt normal water ice. By June and July, we started to get the first clear look at its chemical makeup. This is where the portrait of the traveller became truly alien. We use light analysis, a process called spectroscopy, to determine what things are made of in space. When 3I Atlas passed in front of distant stars, or when sunlight hit its dusty tail instruments on Earth, broke that light down into a rainbow of colours to read the chemical signature. The results were shocking. The reading showed an incredibly high concentration of carbon dioxide. While comets in our solar system do contain carbon dioxide, the amount coming off 3I Atlas was massive. It was bleeding this gas into space at a rate that suggested it was born in a place far colder and darker than the fringes of our own sun's influence. It was a snowball made of dry ice created in a stellar nursery different from the cloud of gas that built the Earth. It was a time capsule from a frozen, distant world. But the carbon dioxide was not the biggest surprise. The detail that kept scientists awake at night was the heavy metal. In August, as the object picked up speed and raced closer to the inner planets, sensitive detectors picked up the clear, undeniable signature of nickel vapor in the cloud surrounding the comet. This should not have been possible. In our experience, nickel exists inside comets, but it usually stays locked deep in the rocky core until the comet gets very, very close to the sun, so close that the heat is intense enough to vaporize metal. 3I. Atlas was nowhere near that hot, yet there it was, a ghost of glowing nickel surrounded by a cloud of carbon dioxide. This combination was the smoking gun. It suggested that the chemistry of this object was fundamentally wrong for our neighbourhood. The ratio of iron to nickel and the way these metals were being released at such low temperatures was like finding a tropical flower growing in the middle of Antarctica. It was a chemical recipe cooked up around a different star. It proved that 3I Atlas was not a local rock that had simply drifted. It was a visitor that had travelled a very long way. Then came the great spectacle of October. The date was October 3rd, 2025. This was the day the traveller came to visit our neighbour. The trajectory of 3I Atlas brought it into a close flyby of the planet Mars. For weeks the anticipation was building. We were not just watching from Earth. We turned every camera we had in orbit around Mars to face the visitor. It was a cosmic near miss. From the surface of Mars, if you were standing there, 3I Atlas would have looked like a second fuzzy moon glowing with a ghostly green and blue light against the pink Martian sky. The green colour came from the burning carbon gases, while the blue tint came from the ionized molecules interacting with the solar wind. It was a hauntingly beautiful sight, a silent lantern drifting through the dark. The flyby gave us the most precise data on its physical shape. It was not round. It was elongated, stretched out like a cigar or a shard of broken glass. This shape is typical for objects that have drifted through interstellar space for millions of years. Tumbling through the void shaped by cosmic rays and ancient collisions, it looked like a piece of wreckage from a galactic accident. It was roughly 400 meters long, tumbling end over end in a slow hypnotic rhythm. During the Mars encounter, the gravity of the red planet pulled hard at the comet. Scientists watched closely, hoping to see the comet break apart or change course drastically. Many comets are fragile, like loose collections of gravel. But 3I Atlas was dense and sturdy. It shrugged off the pull of Mars, adjusting its path only slightly. This sturdiness was another clue. It It was not a fluffy ball of snow, it was a solid, hardened traveller that had survived a journey of light years. This period from the discovery of the nickel in August to the visual drama of the Mars flyby in October defined the personality of 3I Atlas. It was not a passive rock. It was active, spewing gas and metal changing colours and moving with a speed that proved it was not bound to our sun's gravity. It was an object with a story. By the end of October, as it began to move away from Mars and head toward the inner solar system for its final act, we had our portrait. We knew it was not from here. The chemical accent it spoke with, the heavy nickel, the abundant carbon dioxide, proved it was an immigrant. It was a messenger from a system we will likely never see, carrying the frozen history of a star that might have died long ago. It was beautiful, it was strange, and it was terrifyingly fast. We had built a complete picture of the traveller just in time to watch it disappear forever. October the 29th, 25, marks the defining moment in the long, lonely journey of Comet Atlas. This is the day of perihelion, the point in its elliptical orbit where it comes closest to the Sun. After travelling through the freezing dark of the outer solar system for thousands of years, the comet has arrived at a distance of 60 million miles from the solar surface. While this might still sound like a vast distance to us on Earth, for a fragile object made of ice and dust, it is like stepping directly into a blast furnace. The silence of deep space is replaced by a violent, silent scream of physics as the comet faces the full unshielded power of our star. At this specific distance, the environment changes drastically compared to the space near Earth. The sunlight here is not the gentle warmth we feel on a summer day. It is a ferocious, blinding glare that carries intense radiation. The temperature on the sun-facing side of the comet skyrockets instantly. We are talking about heat intense enough to melt lead, rising hundreds of degrees Celsius in a matter of minutes. This creates a massive temperature shock because the dark side of the comet, the side facing away from the sun, remains frozen in the deep cold of space. This extreme difference, known as a thermal gradient, puts the comet under immense physical stress. It is like pouring boiling water into a frozen glass. The structure wants to shatter. To understand what is happening to the comet, we must remember what it actually is. Astronomers often call comets dirty snowballs. They are not solid rocks like asteroids. They are loose collections of ancient water ice, frozen carbon dioxide, frozen ammonia, and dust particles, all held together by weak gravity. As Atlas hits the 60 million mile mark, these frozen materials do not melt into liquid water like an ice cube on a table. Because there is no air pressure in space, they undergo a process called sublimation. This means the ice turns directly from a solid into a gas. This sublimation is the engine of the comet's transformation. Deep inside the comet's core, pockets of ancient gas that have been trapped since the formation of the solar system begin to wake up. The heat penetrates the outer crust, warming these buried ices. As they turn to gas, they expand rapidly. In physics, we know that gas takes up much more space than solid ice. This expansion creates tremendous internal pressure. The gas pushes against the rock and dust surrounding it, looking for a way out. When the pressure becomes too high, it blasts through the comet's surface. These are not small leaks. They are explosive jets of gas and dust shooting out into space like geysers. These jets act like small rocket thrusters, causing the comet to spin, tumble, and wobble unpredictably. While the heat attacks the comet from the outside, another invisible force is at work, the Loeb effect. This is a principle of orbital mechanics that describes how energy works when an object falls into a gravity well. As Comet Atlas dives toward the Sun, it is trading its potential energy, the energy it had by being high up and far away, for kinetic energy, which is the energy of motion. October 29th represents the peak of this trade. The comet is moving faster now than at any other point in its orbit. It is falling down the steepest part of the Sun's gravity well. The Loeb effect dictates that a change in speed is most effective when the object is moving fast. At perihelion, the Sun's gravity whips the comet around the curve of its orbit at staggering speeds, reaching tens of thousands of miles per hour. This is not just a gentle turn, it is a violent slingshot. The comet feels a massive gravitational yank. The Sun grabs the comet and swings it around, changing its direction sharply to send it back out into the solar system. This immense speed is the only thing keeping the comet from falling directly into the Sun and being vaporized. It is a perfect, delicate balance between the speed trying to fling it out and the gravity trying to pull it in. However, gravity does not pull on the entire comet evenly. This brings us to the concept of tidal forces. Because the Sun is so massive and the comet is relatively close, the gravitational pull on the front of the comet, the side facing the Sun, is stronger than the pull on the back of the comet. Even though the comet is small, this difference in force creates a stretching effect. It is as if invisible hands are holding the front and back of the comet and pulling them in opposite directions. For a solid planet like Earth, these tidal forces just move the ocean water, creating tides, but for a dirty snowball that is loosely packed together, these forces are dangerous. They threaten to rip the comet apart. The structural integrity of Comet Atlas is being tested to its limit. The glue holding the rocks and dust together is just frozen ice, and that ice is rapidly disappearing into gas. If the tidal forces become stronger than the comet's own weak gravity holding it together, the nucleus could fracture. It could split into 2 or more pieces, or in a worst-case scenario completely disintegrate into a cloud of dust, ending its journey forever. As the comet survives the closest approach, the cloud of gas and dust around it, the coma swells to its maximum size. It becomes a massive glowing halo. The pressure from the sunlight, literally the physical push of photons hitting dust particles, blows this material backward to form the iconic tail. At perihelion, this tail is at its brightest and most dynamic. The comet is shedding mass at a rate of tons per second. It is literally bleeding its own body mass into space to survive the heat. The encounter on October 29 is a battle for survival. It is a clash between the binding energy of the comet and the disruptive energy of the sun. The heat tries to vaporize it, the internal pressure tries to explode it, the tidal forces try to tear it apart. If Comet Atlas survives this passage through the furnace, it will emerge changed. It will be smaller, scarred, and spinning differently, carrying the history of this fiery encounter as it begins its long climb back into the cold darkness of the outer solar system. This is not just a movement through space, it is a violent physical metamorphosis. In the vast theatre of space exploration, we often focus on the hardware, the thrusters, the antennas, and the nuclear batteries. But there is another component that is just as critical, though it cannot be touched or measured by sensors, the human mind, and specifically its capacity to endure the unknown. When Voyager 1 began sending back nonsensical data instead of clear information, it did not just break a circuit, it broke a psychological rhythm that we have come to rely on for nearly 5 decades. This period of troubleshooting brought us face to face with the profound, heavy nature of silence. To understand the weight of this silence, we must look back before we look up. We must remember a time when silence was a natural part of the human experience. Think of the great explorers of the 15th and 16th centuries. When a wooden ship left the harbour in Lisbon or Plymouth, bound for the New World or the Spice Islands, it was severing the cord of communication completely. There were no satellites to track their path, no radios to report their status. When those sailors sailed over the horizon, they effectively disappeared from the world of the living for months, sometimes years. The families left behind on the shore had to live with a deep, abiding silence. They had to cultivate a specific kind of patience, a faith that just because they could not see the ship, it did not mean the ship was lost. In those days, silence was not necessarily an error. It was simply the reality of distance. A letter might take 6 months to cross the ocean, and the reply another 6. The gap in information was accepted as a part of life. However, the human mind of the 21st century is wired differently. We have largely abolished the concept of waiting from our daily lives. We live in the era of the instant. If we send a text message and do not see the read receipt within a minute, we feel a spark of annoyance. If a website takes 5 seconds to load, we assume it is broken. We have become addicted to the continuous flow of data. We carry devices in our pockets that keep us tethered to a global stream of information that never stops, never sleeps, and never goes silent. This constant connection has created a psychological dependency. We equate connectivity with existence. If something is online, it is alive. If it goes silent, it feels like death. We have lost the muscle memory required to endure silence. We interpret a lack of data as a crisis rather than a natural pause. This is why the silence of Voyager 1 hit the mission team and the scientific community so hard. It forced a group of modern humans accustomed to real-time data to interact with a machine that operates on a timescale that feels ancient. Voyager 1 is so far away, over 24 billion kilometers, that radio signals traveling at the speed of light take about 22.5 hours to reach it. This creates a communication loop that is agonizingly slow. If an engineer at NASA sends a command to the spacecraft on a Monday morning to reset memory, they cannot know if it worked until Wednesday. They must send the command into the void and then simply wait. For 45 hours, nearly 2 full days, they sit in a state of suspended animation. This is the echo of silence. It is a forced meditation. In those 45 hours, there is nothing to do but trust. You cannot hurry the signal. You cannot check the progress, you are subjected to the immutable laws of physics which dictate that light, despite being the fastest thing in the universe, is still not instant. This waiting period creates a unique form of psychological pressure. It is the anxiety of the open loop. The human brain craves closure. It wants to know the result of an action immediately. When that closure is denied, the brain fills the silence with worst-case scenarios. Has the antenna moved? Did the computer crash completely? Is the spacecraft drifting alone in the dark, unable to hear us? The glitch with the flight data system stripped away the comforting stream of binary code, the ones and zeros that usually flows across the screens at mission control. That data stream is the heartbeat of the spacecraft. Even if the data is boring, its presence tells us, I am here, I am working. When that stream turned into gibberish, it was like watching a heart monitor flatline. The connection remained, but the meaning was gone. This disruption forces us to confront a philosophical reality we are not in total control. In our modern lives, we often feel like masters of our environment, because we can summon information for this as food or entertainment with a tap of a finger. But Voyager reminds us of our true scale in the universe. We are small and the distances are vast. No matter how advanced our technology becomes, we cannot defeat distance. We must submit to it. The engineers working on this problem had to adopt the mindset of those ancient sea captains. They had to become comfortable with the unknown. They had to learn to sit with the silence without panicking. It became a test of mental endurance as much as technical skill. They had to send a command into the dark and then go home, eat dinner, sleep and wake up all without knowing if their explorer was still alive. Furthermore, this silence highlights how much we project human qualities onto this robot. We do not just see Voyager as a collection of circuits and aluminum. We see it as a brave little traveller. We feel protective of it. The silence feels personal, like a friend who has stopped answering the phone. The echo of this silence resonates with our own fears of loneliness and isolation. If the most distant object humans have ever created goes silent, the universe feels a little emptier, a little colder. Ultimately, this episode serves as a profound lesson for the modern world. It teaches us that silence is not always empty. In the silence between the command and the reply, there is hope. There is the dedication of the people refusing to give up. And there is the realization that some things, great things, cannot be rushed. The silence of Voyager is a mirror. It reflects our modern anxiety about disconnection, but it also reflects the timeless human capacity to reach out into the dark, wait for an answer, and believe that the voice will return. It reminds us that in the vastness of the cosmos, the connection itself is a miracle, and the silence is the price we pay for exploring the edge of forever. When we leave the solid ground of proven science and step into the vast silent void between the stars, the conversation inevitably changes. It shifts from data and hard facts to something softer, more mysterious and deeply human. This is the realm of speculation where the line between advanced astrophysics and science fiction begins to blur. We call these whispers in the dark. These are the anomalies that we cannot quite explain, yet the strange occurrences that make even the most rational scientists pause and ask, what if? One of the most compelling modern discussions regarding alien technology centers around a strange visitor named Oumuamua. In October 2017, astronomers in Hawaii detected an object passing through our solar system. It was not like the asteroids or comets we usually see. It was moving too fast to be trapped by the sun's gravity, which meant it came from somewhere else in the galaxy. It was our first confirmed interstellar visitor. But the speed was not the only strange thing. As Oumuamua moved away from the sun, it accelerated. Comets do this when the sun heats them up and they release gas acting like a rocket engine. However, telescopes did not see any tail of gas or dust behind Oumuamua. It was also tumbling through space and had a very unusual shape, likely long and thin like a cigar or flat like a pancake. This brings us to the controversial perspective of Professor Avi Loeb, a former chair of astronomy at Harvard University. While most scientists argued that Oumuamua was likely a strange natural rock, perhaps a hydrogen iceberg or a dust bunny formed in space, Loeb offered a different, more provocative hypothesis. He suggested that the acceleration could be artificial. He proposed that Oumuamua might be a piece of extraterrestrial technology, specifically a light sail. A light sail is a type of propulsion that uses the pressure of sunlight to push a spacecraft, much like wind pushes a sailboat on the ocean. If Oumuamua was a thin artificial sail, the sunlight pushing against it could explain why it sped up without burning fuel. Loeb argues that we should not be afraid to consider this possibility. He believes that the scientific community is often too conservative and that, by dismissing the alien option too quickly, we might miss evidence that is right in front of our eyes. His view is not that it definitely was aliens, but that we must leave that door open until we have proof otherwise. But why does this idea excite us so much? Why do humans have such a deep hunger to find artificial signs in the universe? The answer lies in our psychology. Looking at the universe is a humbling and sometimes terrifying experience. We live on a small blue rock floating in an endless sea of darkness. The silence of space is heavy. If we find a radio signal, a laser flash, or a piece of broken machinery, it would mean the silence is broken. It would mean we are not the only ones who can build, think, and dream. It solves the problem of cosmic loneliness. Furthermore, finding alien technology, even if it is from a dead civilization, would act as a mirror for humanity. It would prove that technological civilizations can survive for a long time. Right now, we are worried that our own technology, like nuclear weapons or climate change, might destroy us. Finding a relic from an older species would give us hope that it is possible to survive our own technological adolescence. However, science demands that we keep our emotions in check. We must look at the evidence with a cool, rational eye. Throughout history, we have heard many whispers that turned out to be natural events. Take the famous WOW signal detected in 1977. A radio telescope picked up a strong narrow-band radio signal coming from the constellation Sagittarius. It lasted for 72 seconds and was so unique that the astronomer Jerry Amon wrote "Wow" on the printout. For decades, people hoped this was a message. However, recent science suggests it was likely caused by a pair of comets passing by. Comets are surrounded by huge clouds of hydrogen gas. Hydrogen emits radio waves at a frequency of 1,420 MHz, the exact frequency of the WOW signal. It wasn't a greeting. It was likely just nature speaking in the language of chemistry. Then there are the fast radio bursts, or FRBs. These are incredibly powerful flashes of radio energy that last only a few milliseconds. When they were first discovered, they were so bright and fast that some speculated they could be the exhaust from giant alien starships accelerating to light speed. It was a romantic idea. But as we built better telescopes, we found the true culprit, magnetars. A magnetar is a type of neutron star, the dead core of a massive star that has exploded. These stars have magnetic fields trillions of times stronger than Earth's. Sometimes the crust of these stars cracks under the magnetic pressure, causing a starquake. This release of energy creates the massive blast of radio waves we see as an FRB. Once again, what looked like a technological beacon turned out to be a violent natural event. We also have the mystery of Tabby's star. A few years ago, astronomers noticed that the light from a star named KIC 84628552 was dipping in a very strange pattern. It wasn't just a planet passing in front of it. The light would drop by 20% and look chaotic. Speculation ran wild. Could it be a Dyson sphere? A Dyson sphere is a hypothetical megastructure built by a super advanced civilization to surround a star and harvest all its energy. If a civilization built a massive shell of solar panels around their star, it would block the light in irregular ways. It was a thrilling theory. But after further study using different types of light infrared and ultraviolet, scientists realized that the dimming was caused by fine dust. If it were a solid structure like a Dyson sphere, it would block all colors of light equally. Instead, the blue light was blocked more than the red light, which is exactly what happens when light passes through a cloud of dust. The alien megastructure was likely just a swarm of dusty comets or the debris from a smashed moon. This pattern teaches us an important lesson. The universe is noisy. Stars explode, black holes collide, and magnetic fields twist and snap. Nature is capable of creating phenomena that mimic technology. When we hear a whisper in the dark, our instinct is to ask, who is there? But the rational scientist must first ask, what is that? We apply a principle called Occam's razor, which states that the simplest explanation is usually the correct one. A cloud of hydrogen gas is a simpler explanation than an interstellar radio transmitter. A cloud of dust is simpler than a giant alien power plant. However, this does not mean we should stop listening. The search for techno-signatures, signs of technology, is more active than ever. We are scanning the sky for laser pulses, industrial pollution in the atmospheres of distant planets, and heat waste from megastructures. We listen not because we have found something, but because we haven't found it yet. The whispers in the dark are currently just that, whispers of nature echoing through the galaxy. But we keep our ears open. We analyze every anomaly and chase every ghost signal. We do this because while 99 times out of 100, it will be a rock or a star, we only need to be right once. And until then, we remain curious, skeptical, and ever watchful in the long, quiet night of the cosmos. The sound of silence. To the public, the days following a potential anomaly on Mars often feel like a vacuum. On social media, the image is being shared millions of times per hour. Forums are exploding with theories of all, ranging from ancient civilizations to simple rocks. Yet if you navigate to the official websites of NASA or the European Space Agency ESA, the front page likely shows a standard update about a weather report or a scheduled antenna maintenance check. This disconnect creates a massive tension. Why is the world screaming while the people in charge are whispering? To understand this, we must look away from the red planet and look inside the meeting rooms of Washington, D.C. and Paris. The silence is not empty, it is heavy. It is the silence of a library where people are reading very important books, not the silence of an empty room. The machinery of caution. Space agencies like NASA and ESA operate on a timeline that is completely different from the internet. The internet moves at the speed of a click, science moves at the speed of verification. These organizations are funded by tax money and are responsible to their governments. Their primary currency is not attention, it is credibility. If a YouTuber analyzes a Mars photo and claims it is a statue, and they're wrong, they might get some angry comments, but they get to keep their views. If the NASA administrator calls a press conference to announce the discovery of life and they are wrong, the agency could lose funding, the leadership could be fired, and the reputation of scientific inquiry could be damaged for a generation. Therefore, the first rule inside these agencies is the null hypothesis. In simple terms, this means they assume the discovery is not real until every other possibility is destroyed. When a rover sends back data that looks like a structure or a biological fossil, the immediate reaction inside the Mission Control Center is not joy, it is suspicion. The engineers do not say we found aliens, they say what is wrong with the camera. The internal process, red teaming. Before a press release is even drafted, the data goes through a brutal internal process. First, the engineering team looks at the hardware. They check the temperature of the camera sensor. Was it too hot? Was it too cold? Could a cosmic ray, a high-energy particle from space, have hit the sensor and created a dead pixel that looks like a light or a geometric shape? They check the compression algorithms. When an image is sent from Mars to Earth, it is squeezed down to save space. Sometimes this squeezing process creates digital artifacts which are like visual glitches that look like real objects, but are just computer errors. If the hardware checks out, the data moves to the geology team. They look at the lighting. Is this a shadow being cast by a normal rock at a weird angle? The sun on Mars behaves differently than on Earth because the atmosphere is full of dust. This dust scatters light in ways that can trick the human eye. A rock that looks like a face at noon might look like a flat stone at sunset. Only after the engineers and the geologists have tried to prove the image is fake and failed does the conversation move up the chain of command. This process can take weeks or even months. During this time, strict non-disclosure agreements are signed. This is not necessarily to hide the truth, but to prevent a leak of partial information that could be misunderstood. The fear of the false positive history haunts these agencies. In the 1990s, scientists found a meteorite from Mars in Antarctica, AL 84001. They announced that it might contain fossilized bacteria. It was a massive global event. The President of the United States even gave a speech about it. Years later, most scientists concluded that the shapes were likely caused by non-biological chemical processes. The excitement faded and the general public felt disappointed, even tricked. NASA learned a hard lesson that day. You do not announce maybe. You only announce definitely. This fear of a false positive announcing a success that turns out to be a failure is the primary driver of the silence. In the scientific method, an extraordinary claim requires extraordinary evidence. A picture is not extraordinary evidence. They need chemical analysis, thermal data, and perhaps a second photo from a different angle. Getting the rover to turn around and go back to a specific rock can take days of programming. Every command takes nearly 20 minutes to travel from Earth to Mars. Nothing happens quickly. Managing global panic. There is also a psychological and sociological component to the silence. This is where the Brookings Report mentality comes into play. While the idea that the government thinks people can't handle the truth is often exaggerated by conspiracy theorists, there is a kernel of truth to it. Agencies like NASA and ESA are deeply aware that confirmation of intelligent life or even the ruins of a past civilization would be the most significant moment in human history. It would affect religion, philosophy, and politics. They want to ensure the message is controlled accurate and calm. If they release raw data without context, the public might panic or misinterpret the findings. For example, if they find a weird gas in the atmosphere, they don't want headlines saying aliens are attacking. They want headlines saying atmospheric anomaly detected, further study required. To achieve this, they draft statements carefully. Every word is argued over. A sentence might be changed from indicates life to suggests potential biological processes. This bureaucratic polishing takes time. It is boring, it is slow, but it's designed to be safe. Strategic silence versus cover-up. It is crucial to distinguish between strategic silence and a cover-up. A cover-up implies malice. It implies that the organization knows the truth, wants to keep it for themselves, perhaps for military technology or power, and is actively lying to the public to lead them away from the answer. A cover-up involves destroying evidence or faking data. Strategic silence is different. It implies that the organization suspects the truth but is terrified of being wrong. They are not hiding the data to keep it for themselves. They are holding the data until they understand what it actually means. They are silent because they are working, not because they are plotting. In a cover-up, the goal is that the public never knows. In strategic silence, the goal is that the public knows eventually, but only when the facts are 100% solid. However, to the outside observer, these two things look exactly the same. Both result in a lack of information. Both result in no comment from officials. This similarity is what fuels the conspiracy theories. When a spokesperson says, "We are currently analysing the data and have no comment at this time," the skeptic hears, "We are hiding the aliens." The scientist actually means, "We are arguing about rock shadows and don't want to look stupid." The human element. Finally, we must remember that the institutions are made of people. There are project managers who are afraid of losing their pensions. There are scientists who have spent 30 years studying red rocks and are terrified that their life's work might be overturned. There is also the giggle factor. For decades, any scientist who talked about aliens was laughed at. It was considered a career killer. Even today, serious astrobiologists are very careful. They do not want to be associated with tabloid newspapers or sci-fi movies. They want to be respected by their peers. So when a strange image appears, the human reaction inside NASA is not just curiosity, it is anxiety. They know the world is watching. They know that if they speak, they cannot take it back. The silence you hear from the institutions is not the sound of a door being locked. It is the sound of 1,000 scientists holding their breath, checking their math, recalibrating their sensors, and typing out drafts of a press release only to delete them and start over. Because for the first time in history, they have to be absolutely, undeniably perfect. For centuries, humanity looked up at the night sky and believed that our solar system was a lonely island. We thought that everything moving around our sun, the planets, the asteroids, and the comets was born here and would die here. We believed we were isolated from the rest of the galaxy by a vast empty ocean of darkness. That belief ended in October of 2017. To understand the gravity of the arrival of 3I Atlas, we must first look back at the history of interstellar visitors. Atlas is not the first guest to enter our home, but it is by far the most significant. It represents the third chapter in a story that is slowly revealing the chaotic and diverse nature of the Milky Way galaxy. The first messenger 1I, Oumuamua. The era of interstellar astronomy began with a flash of light recorded by the Pan-STARRS telescope in Hawaii. Astronomers spotted an object moving much too fast to be trapped by the sun's gravity. They named it 1I, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Oumuamua was a shock to the system. Before we saw it, astronomers had models predicting what an interstellar object should look like. They expected it to look like a comet, a dirty snowball thrown out of another star system. We expected to see a tail of gas and dust trailing behind it. Oumuamua broke every rule. First there was its shape. As it tumbled through space, its brightness changed wildly, suggesting it was incredibly elongated, perhaps 10 times longer than it was wide. Artists depicted it as a cigar or a flat pancake, a shape unlike anything seen in our own system. Second, it was dry. There was no visible tail, no cloud of gas, and no dust. It looked like a dead rock, possibly made of metal, or rock rich in certain carbon baked by cosmic radiation over millions of years. But the biggest mystery was its movement. As Oumuamua moved away from the sun, it accelerated. It moved faster than gravity a zone could explain. In a normal comet, this is caused by ice turning into gas and acting like a rocket thruster. But Oumuamua had no visible gas. This non-gravitational acceleration sparked wild theories. Was it a hydrogen iceberg that was invisible to our sensors? Was it a dust bunny made of ultralight material? Or, as some dared to whisper, was it an artificial light sail sent by another civilization? We never got a final answer. Oumuamua was small fast and vanished into the dark before we could catch it. It left us with more questions than answers. The second messenger, Tuai Borisov. 2 years later, in August of 2019, the alarm rang again. An amateur astronomer named Gennady Borisov spotted an object moving at a high speed and a strange angle. This became Tuai Borisov. If Oumuamua was the mysterious stranger, Borisov was the familiar cousin. Unlike its predecessor, Borisov looked exactly like we expected. It was a rogue comet. It had a beautiful fuzzy atmosphere known as a coma and a distinct tail. Spectroscopic analysis reading the light bouncing off the object told us it was made of familiar things: carbon monoxide and water. This was a comforting discovery. It told us that other star systems possess the same building blocks as our own. The chemistry that created Earth and our oceans is not unique to us. It is happening everywhere. Borisov was likely ejected from a system dominated by a red dwarf star thrown out by a giant planet and drifted for light years until it reached us. It was ghostly fragile and completely natural. The third messenger, 3I Atlas. Now we stand in the shadow of the third visitor, 3I Atlas. If Oumuamua was a scout and Borisov was a ghost, then Atlas is a titan. By placing Atlas alongside the previous two, we see a terrifying progression. Oumuamua was roughly 100 to 400 meters long. Borisov was less than 1 kilometer wide. Atlas, however, operates on a scale that dwarfs them both. Atlas resolves the paradox of the first two visitors. It combines the solid, coherent structure of Oumuamua with the volatile activity of Borisov, but with a density and mass that suggests something far more permanent. Comparing their trajectories gives us a clue to their origins. Oumuamua came from the direction of the star Vega, dropping into our system from above the planetary plane. Borisov came from the constellation Cassiopeia. Atlas approaches with a trajectory that suggests it did not just fall here by accident. Its path implies a gravitational capture or a very specific injection orbit. While Oumuamua sped up mysteriously and Borisov drifted passively, Atlas dominates its environment. Its interaction with the solar wind and magnetic fields is creating a bow shock, a wave of energy that neither of the previous visitors produced. The rule of diversity. Is there a common law for these interstellar objects? For a long time, scientists searched for a single template. They thought all visitors would be icy comets. When Oumuamua arrived, they had to rewrite the books. When Borisov arrived, they had to rewrite them again. Now, with the arrival of Atlas, we must accept a new truth: diversity is the rule. The Milky Way contains between 100 billion and 400 billion stars. Some are like our sun, hot and yellow. Some are red and dim, some are dead white dwarfs. Each of these stars creates a planetary system with a unique history. Oumuamua likely came from a violent system where a planet was shredded by tidal forces, creating long shards of rock. It is a piece of planetary debris, a scar from a cosmic accident. Borisov came from a calm, cold outer edge of a system gently nudged away. It is a pristine sample of a stellar nursery. Atlas represents a third category. It is not a shard and it is not a snowball. Its size and composition suggest it might be a planetesimal, a baby planet, that was kicked out of its home before it could finish growing. Or perhaps it is a captured moon from a rogue planet that is passing by in the darkness unseen, a galaxy of debris. These three visitors tell us that the space between stars is not empty. It is a highway filled with the wreckage of planetary formation. For every star in the sky, there are likely trillions of these objects floating in the void. Most are small stones. Some are city-sized rocks like Oumuamua, some are icy comets like Borisov, and extremely rarely there are monsters like Atlas. We are learning that our solar system acts like a net. As we travel around the centre of the galaxy, we sweep up these travellers. For billions of years they have been passing through, but only now with our modern technology have we opened our eyes wide enough to see them. Oumuamua taught us to expect the unexpected. Borisov taught us that the universe shares our chemistry. Atlas is teaching us that the universe can send things that are too big to ignore. The lineage of visitors is no longer a scientific curiosity. With the arrival of Atlas, it has become a matter of survival and understanding our place in the celestial mechanics of the galaxy. We are no longer watching faint lights in the telescope. We are witnessing the convergence of histories. As we observe the object moving away from the sun, passing the point of closest approach known as perihelion, the scientific community must step back from the excitement of science fiction and ground itself in the rigorous discipline of astrophysics. To understand the anomalies we are seeing, whether it is an unexpected boost in speed or a strange tumble in its rotation, we must apply Occam's razor. This philosophical principle suggests that when presented with competing hypotheses, the one that requires the fewest assumptions is usually correct. Before we hypothesize an alien engine, we must exhaust every possible natural mechanism. The physics of outgassing and non-gravitational acceleration. The most robust natural explanation for an object deviating from a standard gravity-driven orbit is the phenomenon of outgassing. This is the rocket effect inherent to comets. A comet is essentially a dirty snowball, a mix of frozen gases, rock and dust. As it plunges toward the inner solar system, the intense heat of the sun penetrates its surface. This thermal energy converts ices directly into gas, a process called sublimation. When these gases escape, they do not seep out gently. They erupt in focused jets. If a jet fires from the sun-facing side of the object, the escaping gas pushes the object in the opposite direction, just like a balloon flying around a room when you let the air out. This creates a non-gravitational acceleration. The challenge with our specific object is that we did not see a massive bright tail, typical of comets like Halley or Hale-Bopp. However, this does not rule out natural causes, it simply refines them. The outgassing could be composed of molecules that are harder to detect with standard telescopes, such as pure water vapor or even molecular nitrogen. If the dust particles released were large, more like gravel than fine powder, they would not reflect sunlight efficiently enough to create a visible tail, yet the momentum transfer would still occur. This dark acceleration is a known, albeit less common behavior in cometary physics. The hydrogen iceberg theory. Expanding on the concept of invisible propulsion, one specific natural hypothesis stands out: the hydrogen iceberg. In the vast freezing nurseries of stars termed molecular clouds, temperatures sit just a few degrees above absolute zero. In these environments, hydrogen can freeze solid. If our visitor is a chunk of solid hydrogen, the physics of its passage near the sun fits the data beautifully. As hydrogen ice sublimates, it turns into transparent hydrogen gas. Our current telescopes would not easily see a cloud of hydrogen, explaining the lack of a visible tail. Furthermore, hydrogen is extremely light. The energy required to push a hydrogen object is significantly less than what is needed for a rocky asteroid. This means the solar heating it experienced at perihelion would generate exactly the kind of smooth, powerful acceleration we observed. While a solid hydrogen object has never been definitively seen before, it is a theoretically sound prediction that fits the natural criteria without needing artificial technology. Tidal forces and fragmentation. Another scenario that applies Occam's razor effectively is the physical breakup of the object. The gravitational pull of the sun is immense. As an object swings around the star at speeds exceeding 100 km per second, it experiences massive tidal forces. These are the same forces that cause tides on Earth, but on a scale capable of solid rock. If the object is a rubble pile, a common structure for asteroids where the body is just a loose collection of rocks held together by weak gravity, the sun's gravity could stretch and distort it. This distortion can change the object's center of mass, altering its trajectory in a way that mimics acceleration. Furthermore, we must consider fragmentation events. It is possible that a small piece of the object broke off during its close flyby. If the object ejected a large boulder or a slab of crust, the action-reaction principle, Newton's third law, dictates that the main body would receive a kick in the opposite direction. If the fragment was small and dark, we might have missed it entirely, seeing only the resulting change in the main body's path. This is a violent, chaotic, but entirely natural death throw of a celestial body. Rotational instability and the Loeb effect. We also observed that the object's brightness fluctuated wildly, suggesting it is tumbling end over end rather than spinning smoothly. In a natural context, this is often explained by the Loeb effect, Yarkovsky-O'Keefe-Radzievsky-Paddock effect. This is a phenomenon where sunlight heats up one side of an irregular object. As that side rotates into the shadow, it radiates heat away as thermal photons. Believe it or not, light carries momentum. As these heat photons shoot off into space, they impart a tiny, tiny torque to the object. Over millions of years, or during an intense pass by the sun, this can spin an object up until it spins so fast it threatens to fly apart, or it can cause the chaotic tumbling motion we observe. Additionally, if outgassing jets are not aligned perfectly with the object's center of mass, they will act like attitude control thrusters gone wrong, sending the object into a complex spin. A chaotic tumble is exactly what we would expect from an active dying comet that has lost its structural integrity rather than a stabilized alien probe, surface evolution and space weathering. Finally, we must look at the surface itself. The object appeared reddish and dark. This is a classic signature of space weathering. When organic-rich ices containing carbon are bombarded by cosmic rays and solar wind for millions of years in deep space, they undergo chemical changes. The bonds break and reform, creating a complex tar-like crust called tholins. This dark red crust acts as an insulator. When the object hit perihelion, the heat had to penetrate the thick, tarry skin to reach the ice below. This can result in a delayed reaction. Instead of outgassing steadily like a fresh comet, the pressure builds up under the crust until it bursts through in a sudden, violent vent. This would explain why the acceleration might seem erratic or why the brightness changes are hard to predict. It is a natural protective mechanism of old comets, not a camouflage shield. Conclusion. The logic of nature. When we look at the sum of these parts, invisible outgassing hydrogen composition, tidal stress and space weathering, we find that we can reconstruct the object's behavior without invoking extraterrestrial intelligence. Nature is capable of producing objects that are thin, elongated and fast. Nature is capable of creating engines through the sublimation of ice. By adhering to Occam's razor, we accept that while the alien light sail hypothesis is exciting and cannot be strictly disproven, yet the exotic comet hypothesis fits the laws of physics as we know them. It requires us only to accept that we have seen a type of natural object we haven't seen before, rather than a species of intelligence we haven't met before. Until we have undeniable proof of the artificial, the cosmos offers enough mystery in its natural geology to explain the events following perihelion. If we step back from our small neighbourhood, the Sun, the Earth, and our sibling planets, and look at the bigger picture, the view changes dramatically. We stop seeing the solar system as a fortress with high walls. Instead, we begin to see it as a small clearing in a vast ancient forest. This forest is the Milky Way galaxy. For a long time, humans believed that stars were islands separated by oceans of emptiness that nothing could cross. We thought that what happened in our solar system stayed here, and what happened around a distant star stayed there. But the arrival of interstellar visitors like Oumuamua has shattered that illusion of isolation. We are now waking up to a beautiful and profound truth: we live in a galactic ecosystem. Just like a forest on Earth has weaned birds and rivers that carry seeds and pollen from one tree to another, the galaxy has its own way of moving material around. It is a living, breathing system where nothing is truly stagnant. This brings us to one of the most fascinating ideas in science, the theory of panspermia. The word sounds complex, but the idea is simple and poetic. It suggests that life, or at least the chemical seeds required for life, is not unique to Earth. Instead, these seeds are scattered throughout the universe. Think of the galaxy as a giant garden. In this garden, comets and asteroids act as the gardeners, or perhaps the bees. They are the cosmic transporters. When a solar system is forming, it is a chaotic and violent place. Giant rocks smash into each other and gravity throws huge amounts of debris out into the deep freeze of interstellar space. These ejected rocks, billions and billions of them, drift through the dark for millions of years. They become interstellar travelers. But they are not just dead rocks, they are cargo ships. Deep inside the ice of these comets, protected from the harsh radiation of stars, lie the ingredients of life. We are talking about water, carbon, and complex organic molecules. Scientists have already found amino acids, the building blocks of proteins on meteorites that fell to Earth. If we imagine these interstellar objects as capsules, they carry the chemical memory of their home system. This changes how we view an object like Oumuamua. It was not just a random stone tumbling through the dark, it was a connection. It was a piece of a distant world that physically entered our home. It brings up a meditative question. How many times has this happened before? In the 4.5 billion years of Earth's history, our planet has likely been visited by countless interstellar objects. Some might have just passed by waving hello with their gravity. Others might have crashed into the young Earth, delivering water and organic compounds. It is entirely possible that the very first spark of life on Earth did not start here from scratch. It might have been kickstarted by a seed delivered from a star system that died long before the Sun was born. This concept dissolves the boundaries we place on ourselves. It suggests that biology is not a miracle that happened once on a lonely blue rock. Instead, biology might be a fundamental property of the universe waiting for the right conditions to bloom. The galaxy is constantly mixing its ingredients. Consider the life cycle of the stars themselves. When a massive star reaches the end of its life, it does not just fade away, it explodes in a supernova. This explosion is a massive factory. It takes simple atoms like hydrogen and helium and fuses them into heavier elements: carbon, oxygen, iron, gold, and nitrogen. These are the elements that make up your blood, your bones, and the air you breathe. When the star explodes, it blasts these new elements out into the galaxy in great clouds of dust and gas. Over time, gravity pulls this dust together to form new stars and new planets. The waste of one star becomes the body of the next. This means that the atoms in your right hand might have come from a different star than the atoms in your left hand. We are physically made of stardust that has been recycled through the galactic ecosystem. In this view, there is no such thing as empty space. The space between stars is filled with these drifting seeds, dust grains, and gas clouds. It is a web of connection. The gravity of the Milky Way binds us all together in a slow, majestic dance. Every star you see in the night sky is influencing every other star, however slightly. This perspective is deeply meditative. It cures us of cosmic loneliness. We often look up and feel small, thinking we are isolated in a cold, indifferent void. But the galactic ecosystem tells us we are part of a grand, warm cycle. We are the children of the galaxy, not just the children of Earth. If Oumuamua was indeed a natural object, it was a messenger reminding us of this flow. It showed us that the galaxy is busy. There is traffic out there. Rocks are moving, dust is flowing, and chemistry is happening in the dark. If we embrace the idea of panspermia, we must accept that we have relatives among the stars. If the seeds of life are common and the delivery system, comets and asteroids, is efficient, then life should be the rule, not the exception. We might be distinct from life on other planets, just as an oak tree is different from a pine tree, but we grow from the same soil and drink the same rain. This realization invites a sense of humility and wonder. We are not the center of the universe, but we are an intimate part of it. The iron in our blood was forged in the hearts of giants. The water in our glass might have arrived on a comet that traveled light years to get here. As we look forward to the future of space exploration, we are not just exploring the unknown, we are tracing our heritage. We are following the breadcrumbs back through the dark forest to see where we came from. The interstellar comets are the threads that sew the fabric of the galaxy together. They prove that in the vast, seemingly infinite darkness, everything touches everything else. We are quite literally the universe experiencing itself, connected by a chain of being that stretches across light years and eons. Emerging from the solar glare, as the calendar turns to the first days of November, the astronomical community around the world breathes a collective sigh of relief. For several tense weeks, Comet Atlas has been hidden behind the overwhelming glare of the Sun. This period is known to astronomers as the solar conjunction. It is a blackout zone where no telescope on Earth and no standard observatory in orbit can safely look. The Sun is simply too bright. Pointing a sensitive instrument like the Hubble Space Telescope too close to the Sun would destroy its delicate sensors instantly. During this time, humanity was effectively blind to the status of the comet. We could only wait and trust the mathematical calculations. But now the geometry of the solar system is shifting. By the first week of November, the comet begins to drift away from the Sun's position in our sky. It is moving out of the danger zone and back into the dark velvet of space where we can see it again. This is not just a visual event, it is a resurrection. We are about to find out if the comet survived its fiery encounter with the star. The process of reacquisition. Finding the comet again is not as simple as just pointing a camera at the sky. This process is called reacquisition. It is like trying to spot a tiny moving pebble against a black background, while knowing that the pebble might have broken into 1,000 smaller pieces. The first step involves calculating the new trajectory. The Sun's gravity is immense and it acts like a massive slingshot. As the comet whipped around the Sun at perihelion, its speed increased to hundreds of kilometers per second. Astronomers must update their mathematical models to predict exactly where the comet should appear. If the comet is intact, it will be right where the math says it is. However, if it is fragmented, or if the release of gas acted like a rocket engine pushing it off course, it might be slightly off target. This phenomenon is called non-gravitational acceleration, where the comet steers itself using its own gas jets. Ground-based telescopes in the southern hemisphere usually get the first view. They look for a fuzzy dot in the twilight just before sunrise. Once they confirm the location, the coordinates are sent to the most powerful tools we have, the space telescopes. Hubble, the sharp eye. The Hubble Space Telescope is the first major asset to be deployed for a close inspection. Hubble operates in visible light, the same light our human eyes can see. Its job in early November is to answer the most critical question: is the nucleus still solid? When Hubble points its mirror toward the comet, it is looking for a specific shape. Scientists are hoping to see a bright condensed point of light in the very center of the coma, the cloud of gas around the comet. This is called the false nucleus. If Hubble sees this bright point, it is a celebration. It means the heart of the comet survived the extreme heat. However, the alternative is grim. If Hubble sees a streak of light that looks like a cigar or several small bright dots instead of one big one, it indicates a disaster. That would mean the comet has shattered under the thermal stress. Hubble will also take high-resolution images of the coma to see if there are jets. These are fountains of gas and dust erupting from the surface. If the jets are active and strong, it confirms the comet is alive and healthy. James Webb, the heat seeker. Shortly after Hubble takes its look, the James Webb Space Telescope turns its gold-coated mirrors toward Atlas. James Webb sees the universe differently than Hubble. It looks in the infrared spectrum, which is essentially heat radiation. This capability is crucial for the middle of November. Visible light can be blocked by thick dust, but infrared light goes right through it. James Webb can see through the hazy clouds surrounding the comet to look at the nucleus directly. It measures the temperature of the surface. By analysing the heat, scientists can determine what the surface is made of. Is it covered in dark, crusty dust that holds heat? Or is it exposing fresh, icy material that stays cool? James Webb will also look for the thermal inertia of the comet. This tells us how quickly the comet cools down as it moves away from the sun. A solid rock cools differently than a pile of loose gravel. This data helps scientists understand the density and structure of the object without ever landing on it. Decoding the first data brightness and spectra, once the telescopes lock on the data, starts streaming back to Earth. The first thing astronomers analyze is the light curve. This is a simple graph that shows how bright the comet is day by day. If the line on the graph is steady and slowly fading as the comet moves away, that is considered normal behavior. But if the line is jumping up and down, getting very bright, then very dim, then bright again, it suggests the comet is tumbling uncontrollably. A tumbling comet is unstable and poses a challenge for observation because its surface is constantly changing orientation. The second and perhaps more exciting set of data is the spectra. You can think of this as a barcode for chemicals. By passing the light of the comet through a prism, scientists can see which chemical elements are present. In early November, we expect to see the signature of water vapor, but because the comet was just cooked by the sun, we might see heavier, more complex chemicals that were buried deep inside the ice. We might see signatures of organic molecules, the carbon-based building blocks of life. If the spectrum shows a sudden spike in metallic elements like sodium or iron, it means the dust is evaporating, which only happens at extreme temperatures. This data tells the story of what the comet is actually made of, layer by layer. From waiting to observing. For the mission control teams and scientists around the world, the atmosphere in the room shifts dramatically during this week. For months, they have been in a waiting phase. They were passive observers, hoping that math was right, hoping the comet would not vanish into dust. Now in mid-November, they switch to observing mode. This is an active high-energy phase. The servers fill up with terabytes of images. Computers run hot processing the information. Theoretical physicists have to rewrite their papers in real time based on what the images show. There is a rush to publish the findings. Did the tail disconnect? Did the solar wind rip away the ions? The scientific community becomes a hive of activity. Every pixel of light captured by Hubble and James Webb is analysed for clues. It is no longer about predicting the future. It is about recording history as it happens. The light has returned, and it has brought the secrets of the early solar system back with it. The bright days of December 2025 are beginning to fade. Just a few weeks ago, the comet was the main character of our night sky, a brilliant slash of light that made us stop and look up in wonder. But now the great celestial show is coming to its natural end. The cosmic visitor has finished its business with the sun and the earth. It has survived the intense heat, it has displayed its magnificent tail of dust and gas, and now it turns its back on us to return to where it belongs. As we watch it move night after night, it becomes smaller and dimmer. The gravity of the sun, which once pulled it in with such speed, is now like a slingshot throwing it back out into the deep ocean of space. The comet is not disappearing, it is simply leaving. It is like a ship that came into the harbour to say hello and is now setting sail for the open waters again, moving towards the horizon until it is nothing but a speck of light. The physical changes happening on this mountain of ice and rock are slowing down. When it was close to the sun, the heat was intense. The ice was screaming, turning instantly into gas, creating that beautiful atmosphere that we admired from our backyards. But now, as it travels millions of kilometers away from the warmth, the surface is quieting down. The jets of gas are losing their power. The magnificent tail, which stretched for millions of kilometers across the solar system, is beginning to thin out and fade away. The comet is putting its armor back on. The cold is returning. The silence is reclaiming the rock. It passes the orbit of Mars, the red planet. From the perspective of the comet, Mars is just another silent watcher, a dusty red dot fading in the distance. The comet continues its lonely path heading towards the kingdom of the giants. It will glide past the orbit of Jupiter, the king of planets. It might see the swirling storms and the many moons that dance around the gas giant, but it will not stop. It has enough speed to escape the grip of these massive worlds. Then it will cross the ringed path of Saturn. Imagine the view from the surface of the comet. The sun is no longer a burning ball of fire that dominates the sky. It is becoming smaller, just a very bright star in a sea of darkness. The light is getting weaker. The temperature is dropping to hundreds of degrees below zero. The comet is entering the deep freeze once again. It is a time capsule sealing itself up to protect the secrets of the early solar system for another 1,000 or perhaps million years. This departure brings a heavy but beautiful realization to us down here on Earth. We are reminded of the limits of our own time. The comet does not care about our calendars, our worries, or our busy lives. It operates on a scale of time that we can barely understand. It teaches us a lesson in patience. We waited for years to see it, and the moment of its maximum beauty lasted only a short while. That is the nature of all beautiful things in the universe. They are fleeting, they are temporary, and that is exactly what makes them so precious. We also learn about the vastness of our neighborhood. We often feel that the Earth is huge, but watching this traveler leave reminds us that our home is just a tiny island. The comet is heading out to the Oort cloud, a massive spherical shell surrounding our solar system. This is the true edge of our world, a place so far away that it would take a modern spaceship thousands of years to reach it. The comet will travel through this empty darkness for ages, alone, silent and peaceful. There is a comfort in this departure. It is not a sad goodbye. It is a promise of continuity. The universe is a clock that keeps ticking even when we are not watching. The comet will continue to float, obeying the laws of gravity, perfectly balanced in the void. It does not need fuel, it does not need direction, it simply exists drifting on the breath of the cosmos. Now as you lie there, imagine that you are travelling with it. Let your mind leave the heavy gravity of Earth. Imagine you are weightless, floating just above the surface of this ancient traveller. The noise of the world has been left far behind. There is no sound here, there is no wind, there is only the profound, heavy silence of deep space. Look around you in your imagination. The sky is not blue, it is a deep velvet black. It is softer than any blanket. It wraps around you, comforting and safe. Scattered across this black velvet are millions of diamonds. The stars are steady and unblinking. They are the distant lights of other suns watching over you as you drift. You are moving away from the sun. You can feel the gentle cooling sensation like the cool side of a pillow against your cheek. It is a refreshing cold, a stillness that slows down your heart rate. The frantic energy of the inner solar system is gone. Here everything moves in slow motion. You are gliding, drifting, floating. Picture the comet as a natural spaceship, a cradle of ice. You are resting on it, carried by the momentum of the universe. There is no effort required. You do not need to steer, you do not need to worry about the destination. The path is already set. It is a long, smooth curve that stretches out into the forever. As the comet moves further out, the sun becomes just a tiny point of light, no brighter than the other stars. You are entering the realm of shadow and sleep. The darkness is absolute, but it is not scary. It is the darkness of a restful night, the darkness that comes before a deep restorative dream. Feel yourself drifting deeper into this vast open space. The distance between you and the noise of tomorrow is growing. Millions of kilometers of silence stand between you and your worries. You are protected by the vastness. You are a voyager on a sea of stars, drifting on a calm black ocean that has no waves. The rhythm of the universe is slow and steady, like a pendulum swinging in zero gravity. Back and forth, slow and gentle. You are part of this rhythm now. Your breathing slows down to match the silent glide of the comet. In and out, slow and deep. The journey is long, but there is no rush. You have all the time in the world. You are safe on this journey to the stars. The comet carries you gently into the night, further and further away, drifting into the deep soft blackness, drifting into peace, drifting into silence, drifting into sleep.